Welcome back. Today we are going to delve a little deeper into motion at a constant velocity. In this video, we are going to interpret the data from our experiment to develop a final model for motion at a constant velocity. This final model is going to be an equation that we can use to represent this type of motion. So at this point, you should have already collected position and time data on each of the cars in our video. You should have written down observations that you just visually were able to make about each of their motion. You should have plotted your data on a position versus time graph, so 2 plots, one for each car. Then you should have drawn a trend line for each car. If you have not done this, stop watching this video and actually go do it. Come on, just do it. It will be of great benefit to you as a student to actually practice collecting and analyzing data on your own. Because once we get to class, I will not provide you with my own data that I have analyzed. You will have to collect it all and analyze it all yourself. So yeah, just stop watching, go do it, and then come right back. I'm not going anywhere. If you've already done it, great. We are going to move on right now. So we have this video of 2 cars both moving at a nice constant velocity across a lap track. There are some observations that we can immediately make. We can visually see that they are moving at approximately a constant velocity. We can also see that the white motorcycle is moving at a fast speed and that it is moving to the right, which we can call the positive direction. The blue car, however, is definitely moving at a much slower speed, and it is moving to the left, which we can call the negative direction. There are potentially some other observations that you could have made, but these are the 3 that I want us to focus on. But if you wrote down other observations, that is not wrong. You're just going above and beyond. But if you don't have these written down, make sure you write those down because these are going to end up being really important. When you plot your data on your position time graph, you should get something that looks pretty close to this. Notice, even though the data points aren't perfectly aligned, they still approximate a linear trend. But keep in mind that this was a real-world situation. There is no way for our data to be ideal and perfectly straight. We will talk about a lot of the reasons why it's not perfect as we do labs in class, but don't think you did something wrong if 1 or 2 of your data points are a little off. If the data still looks approximately linear, like mine, then you are good. You collected your data correctly. But if your graphs look nothing like this one, go back and reread the instructions and try to figure out what you did wrong. So after plotting my data, I drew my trend lines, and these trend lines are truly a straight line. These trend lines do not zigzag back and forth in an attempt to hit every single point. It is a single straight line that hits as many points as possible. Again, do not play connect the dots when drawing a trend line. Use a ruler and draw one straight line, hit as many points as you can, but you probably will not be able to hit them all. And this is where you should have gotten to on your own. Now let's look at our results. We should immediately see some similarities and differences between these 2 plots. Let's start with the one similarity between the 2 plots. They are both obviously linear, and there's a reason for this. There's a reason they both show up as linear lines. That is because both cars are undergoing a similar type of motion. They are both moving at a constant velocity. And if you remember, constant velocity shows up as a line on a position time graph. Since both cars are moving at a nice constant velocity, both plots are going to end up being linear. But that's where the similarities between these 2 plots seem to end. We have 2 cars moving in slightly different ways, and we have 2 lines that look slightly different. What we are going to do is try to explain why these plots look so different from each other. And it all has to do with the fact that their motions are different. We've identified these differences down here already. So as we go through this process, keep these differences in mind. We are then going to develop an equation that we can use to represent the motion of these 2 cars based on these differences. The type of analysis that we are about to do is something that we will do for almost every lab throughout the year. So pay attention, not only to the results, but also to the general process that we will be following as we analyze these graphs. So our first step, after we have plotted our data and identified the trend, we are going to start with the general mathematical equation for that trend. In this case, our trend is linear, and the equation for a linear trend or a line is y equals mx plus b. Now, this is literally the vaguest equation that has ever existed. It applies to every single line that has ever existed and ever will exist in our universe. It's no use for our specific situation. What we want to do is customize this very vague and general equation to represent the specific situation we are trying to show here with our very specific lines. So we are going to take all of these generalized variables, y, m, x, and b, and replace them with new ones that actually represent our own situation. The first thing we are going to do is customize our x and y variables. Now, when this equation, y equals mx plus b, represents a line on a graph, the variable y is actually referring to the y-axis, and the variable x is actually referring to the x-axis. But our axes, they're not just general x and y axes that show up in math class, they actually represent real quantities in the real world. So we are going to replace x and y with the appropriate variable so that our equation starts to represent those real quantities as well. So on our graph, our y-axis represents position, and the variable we use to represent position is x. So we can make this replacement here. The variable that our y-axis represents is x, or position. Our x-axis represents time, and the variable we use to represent time is t. So we can make that replacement as well. Okay, our equation is starting to take form. The next thing we need to cover are the values of m and b. And as a reminder, m is the slope of our line, and b is the value of the y-intercept. The values of these two constants, m and b, will come directly from our trend line. We actually have to go to our graph and do some math. We have to calculate the slope by doing rise over run, and we have to look at where does this graph intercept our y-axis. We actually want an equation for both lines, because even though they both share the same x and y-axis values, you might have already noticed the two lines have two different slopes and two different y-intercepts. So they're going to have two different values for m, two different values for b, so they're technically going to have two different equations. I'm going to stop this video here so that we can actually do this math and take a quick break because this video is getting a little long. So at the end of this video, take the time to actually determine the values of the slope and the intercept of each of your trend lines yourself. After you have determined the values, fill in those numbers for m and b. You're going to end up with two different equations for a line in terms of x and t. If you want a little bit of a challenge, try to determine what the units of the slope and the intercept would be, because those numbers that you calculate actually do have units, because all of the numbers on this graph is either going to have a unit of centimeters or seconds. So you have your instructions, calculate these values yourself and get the practice. You'll end up with two equations, one for the blue car and one for the white car. We'll check our answers in the next video.